But okay.
All right, folks. What don't you understand? Why? Why don't you understand about fracking? All right. So the STEM class used what was pretty hardcore. Like we did a bunch of technical things, and then this second term we're kind of doing like the softer side, right? We're doing like STEM soft style, but it's pretty cool because we're learning about like global warming, and we're learning about like fossil fuels and how it's not really that great of an idea to use up all the fossil fuels, and we're kind of being motivated. Well, don't worry, we're going to switch back to hardstyle when we go and do a big project using Python and whatnot. And we're going to be using this textbook called A Bite of Pie, and it's actually pretty cool. And that's the project I want you to start helping me work on. I'm working on it with Mr. Lord on it, and so we're starting that up. So we're not abandoning this curriculum, but I think that this curriculum was good for us to get motivated about what to learn and why we're doing this stuff. But that's pretty much, so I'm going to finish off kind of my last lecture on it. Hopefully I can get through some of this without talking too much story. And I also don't plan on going on forever just because, not to say I want to shortchange you, but I'm exhausted. All right, so this guy was talking to. This is Dr. Richard Alley. He's the guy that we've been following. Pennsylvania State University, or University of Penn State. Is it University of Pennsylvania? It's the University of Pennsylvania. That's right, Pennsylvania State University, and he is a doctor dude, and he is actually pretty awesome. I've been talking to him a lot lately because like he's helping me develop, I'm developing this class based off of this class that he's been developing. So he was talking about how he was talking to these like politicians, and these politicians, and he was telling them about global warming. And then this politician came up to him and says, "I don't know anything about science. I hate science, but I do know that the science that you represent is wrong." And the dude's like, and he kind of has a squeaky voice, doesn't he? He's kind of like, "Well, this is kind of what's going on, folks, right?" So he's like,
kind of like this.
yeah, and he sounds kind of like this on there too. So Dr. Richard Alley said, I guess if you think about it, he's sitting there thinking like, I have a PhD in this stuff. I'm a world leader in this stuff, and you know nothing about science. You came up to me, told me you know nothing about science, and then you're telling me that my science is wrong? Because it's based off of a hockey stick, and that's what she says. It's based off of a hockey stick, and what they mean by a hockey stick is I'll show it to you later. I'll show it to you now. Then it's way down here. This is the hockey stick. There we go. See, looks like a hockey stick. And she was saying that's wrong, and actually, it's not. It's not. It's a well-documented things, and we'll talk about what that is and what that means. But she was saying, "Oh yeah, I saw that graph. I think your graph is broken, so therefore your science is wrong." And what his response to this, and I agree with this, is actually the science that I represent is physics, and it's based off of a lot of physics of atmospheric data. Now, for Tiger and Austin, and actually, you know what, Kalena, I can say that you are now amongst the reins of being a physics student, because you've been doing some hardcore electricity. And to be honest with you, I almost feel like electricity is a little bit more hardcore than mechanics. Because it's a little bit more abstract. Like mechanics I thought was easier. You're doing the hardcore stuff. So you're a physicist too. So what he's saying is like it's based off of this science. And you guys are thinking like, wait a second, when you're teaching us physics, you taught us about mechanics and how things move and all of that kind of stuff. You're teaching us electricity. How is this applying to geoscience? Well, there's a whole branch called geophysics. Physics kind of has its dirty little fingers in everything. But technically, the physics that he's talking about is atmospheric physics. When he's talking about like how the physics of the atmosphere and how that works. And that's a very solid science. So it's not a broken graph. It's not really even an opinion. These are just the facts that they're showing you. And a lot of the preliminary work for this science, where did we get a lot of these facts? Who did all the footwork was actually the U.S. Air Force. Because they were doing the U.S. Air Force isn't necessarily like the agency dedicated to measure global warming, right? They're they're dedicated, and actually you're a serviceman, right?
Yeah.
You're now a serviceman. You're not with the Air Force. You're with the Navy. But I mean, they're dedicated to destroying the bad guys, basically. A part of destroying the bad guys or protecting our borders, which means destroying the bad guys, is they want to develop. They want to make sure that they're spot on with their heat-seeking missiles, right? So they need to measure out the atmosphere. So they did a lot of the science for heat-seeking missiles. They put all these different kinds of sensors, and these sensors are what measuring these things. And then that's basically a lot of the science from global warming comes from this preliminary work of that. So if you want to deny global warming and that kind of stuff, then basically you're telling the Air Force that they put the wrong sensors on their heat-seeking missiles. Have fun with that, my friend. So, it's kind of the science of global warming, and whether or not you believe in global warming or not is basically it's. I don't know. I kind of like the analogy that he used over here, where he says, "All right, asking a scientist whether or not they believe in global warming is like asking whether I take this object and I drop it, will it fall? Yeah, it will fall. There could be a possibility that as soon as I drop this, there could be a tornado or a hurricane that rips off the roof and then causes the thing to fall up. There could have been an earthquake that maybe caused the entire building to collapse and we all fall, and therefore this thing actually kind of goes up, and it seems like it goes up, or it doesn't fall because it falls at the same rate that we're falling at. There could be a giant electromagnetic magnet that is set up and turn on immediately when I drop this, and there happens to be metal particles inside of this plastic cap. I don't know how that works, but it could go up. But in general, you would say,
How?
well, no, I mean, let's pretend it's not a plastic cap. Let's pretend that it's a
Coin.
I kind of want to know why.
There we
it's
go.
metal
This thing right here.
plastic.
There's no metal in a plastic cap. But let's say there was the object that I grabbed was like a
A coin.
Oh,
coin or
just
something like that. Then it would go up or something like that, right? So, for the most part, you would say, okay, I believe in gravity, and it would, you would say, I believe in gravity, and in general, the thing would fall, right? Asking me whether or not the thing would fall downward is pretty much asking whether or not I believe in gravity. Well, to a geoscientist and to these guys who study global warming, if you could see in infrared, you would basically say the same thing. You would say, is global warming real? And then you turn on your infrared glasses on, and you look in infrared, and you look over a couple of years, and you say, definitely, absolutely, it's true. See what I mean? The hard part is putting it all together. We can get these different snippets, but I think that this is the hard part about doing science over long periods of time. Like, you're interested in going into astronomy, right? I just watched this big debate between Bill Nye the Science Guy and Ken Ham the Creationist. Have you guys ever heard about it? Did you hear about that?
Oh my gosh.
Why do you say, oh my gosh? What's going on?
It was basically how to talk around the scientist, and it was not fun if you were on the science side, just because you're too busy going, how is this even happening?
So you watched the debate?
I've heard enough about it such that it's like, no.
Because I watched the debate.
I'm so sorry.
No, I actually quite enjoyed it. But anyway, I watched this debate, and basically, it's kind of hard to describe these things that happened like in the past, because the story of global warming is you're talking about like this graph, right? Let's take a look at that graph that I showed you, the hockey stick. The hockey stick graph apparently was taken over a course of how long? How long did they turn on this? There we go. We've been taking data for the last 10,000 years. What? What? I don't know anybody around 10,000 years ago writing the data like with a little device measuring the concentration of methane gases and the
Ice.
concentration of carbon dioxide in the last 10,000 years ago, writing down his thing, right? And then you pass it off to his son, and 10,000 years later, you're just like, we're still measuring this data. We're still going at it. So how do they do it? And then say, okay, well, we can take ice core samples. And yeah, we can infer back these things. And see, the thing is, to me, when I watch that debate, I'm not going to tell you whether or not I think one guy is right and one guy is definitely wrong and all of that kind of stuff. But let's look at the data. And this is the best we can infer. And I'll let you decide. You folks are intelligent individuals. I mean, you guys are taking one of the hardest classes at MBTA, the electricity class. This one's not as hard. Electricity class is like one of the hardest classes at MBTA, and so you guys are smart individuals. I'm gonna present the information to you, and I'll let you figure it out. Cool. All right. So let's talk a little bit more about energy and the temperature and turning the temperature and all of that kind of stuff. So let's read this short version because I think it's kind of interesting. I think it's very interesting, and then we'll talk about the long version. Short version. The Earth adjusts its temperature to send back to space as much energy as it receives from the sun. But the sun's shortwave energy passes through the air, while some of the Earth's long-wave energy is intercepted by the carbon dioxide. You guys understand what's going on?
Mm-hmm.
All right. Making the Earth warmer and than it otherwise would be, with more warming when more greenhouse gases added to the air. The warmer air picks up the water vapors and melts the reflective snow and ice, making the total warming even larger. So basically, here's what's happening. Okay? I've told you many times before in the past. In fact, this is almost like a reoccurring theme in science, in 8th grade science, in physics, in all of the science I feel like I've taught you guys. What goes in must come out. And he uses this analogy about a factory. Imagine a car factory or an ukulele factory or some kind of factory where you're making something, right? You have something coming in, like parts of a car, tires and all of that kind of stuff coming in. And you have something coming out, finished cars. Cool? So what happens if one is bigger than the other? Like what happens if you have way more parts coming in? Like the shipping guy like was like on crazy mode, and he was like, I'm gonna go beast mode and just like order everything in. Like instead of bringing it in once a week, I'm bringing it in once every day. But you don't hire any workers or any extra things. What's going to happen to your factory? It's going to fill up, and then it's going to explode because there's just too much stuff inside, right? Or what happens if the shipping guy just kind of was like, all right, I'm not going to order anything. I'm going to order it once a month. Well, you're still popping out cars the same rates, but stuff is coming in slower. Your factory is going to run out of stuff, and then you can't pop out stuff. You know what I mean? So ideally, what you would want is the same amount of stuff coming in as there is going out, right? And so essentially that's what's going on with our Earth. The Earth actually receives sunlight, and when it hits the atmosphere, about 70% actually goes into heating the Earth. 30% of the sunlight that we get actually just kind of bounces straight off and gets out of there. Cool? Now, as it passes through the atmosphere, all right, and by the way, we're only talking about a closed system of sunlight. We don't, because you can also say, well, wait a second, don't we actually have an extra amount of energy, not just from sunlight, but from where? From the Earth itself, from the core. Because the core is heating us up. So wouldn't that offset the energy? Essentially, we would radiate more energy going out than the sun has coming in. Does that make sense to you?
It does, but I can't imagine the Earth's core making quite that much.
Well, that's exactly what I'm saying. The Earth's core actually is about 4,000 times smaller as far as heating-wise than how the sun affects us. So yes, there are places that are hot on Earth because of the Earth's core. But, overall, that's teeny compared to what the sun does.
Radioactive ball above us.
Yeah. All right. So, what we can take a look at is this nice burner, and I don't know why he uses this burner. This dude's a doctor, so he has like really nice stuff, and I noticed that like, why the heck is his burner purple?
I think it said something down there. But
Yeah, it did, and it's basically they have like this fancy, easy to clean stovetop, and so come to my house. I'm poor. I've got the burner that's like just like this small, and you turn it on, and it's like black to begin with. And there's no glass on top. And you just burn yourself on it, like straight up. There's no self-cleaning. What is this self-cleaning stuff? You gotta wait till it cools down, take it out, and scrub the coil.
yeah.
Put new tinfoil on it. That's what I do.
Sounds about right.
Yeah. Anyway, you turn that thing on, and what's happening is the coil is taking in electricity. And since we've been talking about electricity, we can talk about it's not a capacitive in there. It's actually a giant resistor. That's what it's called. And we'll talk about that next week when we get into resistors. We've talked about capacitors. We're going to get into resistors. But there's a giant this coil is really just a giant resistor, and it will heat up and it will radiate different wavelengths. And depending on how much electricity you put in, it will radiate different wavelengths. So if you put in a lot of electricity in there, then it will turn like an orange color. But if you put in like even more electricity in there, then it will turn into like a bright reddish, almost yellowish color. Have you ever turned on your stove that high?
I don't think so.
What?
All right. I'm not suggesting you go home and turn on your stove this like, all right, let's go see this.
Unless you're boiling water.
Yeah, unless you're boiling water, then obviously you put it on. You want to boil a pot of tea, then boil a pot of tea. If you could break any kind of safety regulations that they have and put on it, you put down some kind of like drop some kind of insane amount of electricity through there, you probably get that thing to glow white, and maybe even possibly violet at that point. But then at that point, your house would burn down, and that's why they don't let you do that. You would also suck up the electricity and then break all of the fuses inside of your fuse box, and that wouldn't be a good thing either. Your parents wouldn't be down with
Your
that.
house catches on fire if it's violet inside. So the things right here in your house is over there. It can actually.
At the very least, it burns on your stove.
Is
You know
that
what?
much energy conversion?
It wouldn't burn your house down unless something touches it. But what I think that would be more likely to happen is something electrical will break, and that will burn down your house. Have fun with that. All right.
Well, never mind the fact that you'll probably melt your stove long before then.
Yes, you'll melt your stove and anything on it well before that.
I really want to do that.
All right.
Oh, man, if I go to another house that is not mine.
So here's what's happening is we talked. Well, actually, we didn't talk about this at all, and I realized, oh, wait a second, I didn't cover this with you. But you've covered this well, at least I'm covering it in 8th grade. Actually, I shouldn't hit visible light. I want the whole spectrum. Have you guys seen this graph? You've seen these things before? Electromagnetic spectrum, the electromagnetic spectrum and radiation, all of that kind of stuff?
Grade science.
Yeah, 7th grade science. All right.
Oh, really?
Essentially, most of the sunlight that we get is we get a lot of visible light from them. There's actually radio waves that come from the sun. You can actually measure that. In fact, I don't know, did I tell you about how when I was in high school, I built a radio telescope to measure the radio waves happening between Jupiter and Io, but then I would also point it to the sun and then predict sunspots. Did I tell you about that? It's a fun project. It's great.
Uh-oh.
Yeah. Anyway, we get radio waves from the sun. We also get gamma rays. Lucky for us, and we get UV rays. What do UV rays do?
Burn, like give you skin.
They give you sunburn, skin cancers, and that kind of stuff. And lucky for us, our atmosphere actually kicks out most of these guys right over here. These really high.
Where does gamma come from? The sun?
The gamma rays comes from mostly. They can come from nuclear processes, but mostly they come from the sun. That's the stars.
Can that cause like death?
Oh yeah, that's instant death. That's like instant death. You know, that's like, I don't know,
Well, what does it do? Like,
taking cyanide and going chug, chug, chug.
It's probably faster than that.
Yeah.
what does it do?
Yeah. Well,
Can't
one of two things could happen. You will die, or it could turn you into the Hulk.
Oh,
I'm not sure about the Hulk one, but dying, I definitely know that's just probably the most likely thing that will happen. What happens is those gamma rays will actually come in and knock off like parts of your like electrons and parts of your body and that
oh,
kind
so
of
it
stuff.
goes up to the near roots.
Yeah, we're talking about like because it's moving at such a high frequency that it'll actually because like X-rays can pass right through you, right? And they can pass right through you relatively safely. Although they always say relatively safely, and then they put you inside with a lead vest where they don't want you to get stuff, and then they go into the other room and press the button behind a triple pane glass wall or whatever. I get freaked out when they say relatively safely. You're talking about electricity. I'm talking about X-rays. But anyway, we got X-rays, and that passes through you, and that can pass through you without any harm. And your bones are more dense than your fleshy parts, so they can actually see your bones, and that's how you can see your bones. But the gamma rays, if gamma rays pass right through you, that's a big problem. Like that will mutate some of your cells, and then that will kill you because if you're going through cancer, you're going to get radiation. Basically, you're going to die from radiation. You could die almost instantly.
Types of radiation?
Yeah, the different types of radiation, but basically all of the stuff up here is kind of bad, but it's very useful for us. But anyway, we're talking about what happens is the light, the energy that comes in. Remember, I'm telling you that energy that comes in must go out. So energy that the sun gives to the Earth must somehow like use that energy or radiate it out or kick it out or something, because we can't have a build-up in this thing. Well, what is the most energy that we get from the sun is actually in the visible spectrum. It's these wavelengths right over here between infrared and visible. Got it? And those are the shorter wavelengths or higher frequencies, and they actually pass through the atmosphere, no problem whatsoever. When you get into the higher ones of the ultraviolet, and actually I might really have to take this because it might be the quartz system. Oh, it's my wife. Can I call you back? I'm so sorry. I'll call you back at 3 o'clock. Okay, love you, bye. Quartz system might try to be calling me that's for some reason. But anyway, let's move on.
Wrong?
I didn't do anything wrong, and I'm not hiding from them whatsoever. I'm just waiting for their call. There's certain types of UV light that passes through. There's the UVA band, there's the UVB band. UVB, I think, is the one that's bad for you. UVA is the one that gives you, sunburn. So they're both kind of bad for you. But, you also kind of need a little bit of sunlight as well. It provides some advantages for you. But, anyway, the type of energy coming in is mostly in this spectrum, whereas the type of energy that the Earth radiates back is mostly in this spectrum. It's a little bit longer wavelengths.
What? Go
So,
back to that graph.
yo, okay?
It says penetrates Earth's atmosphere. It says no on the ultraviolet, but still we get sun.
Where are you talking about? Penetrates? Oh, okay, here we go.
It says no on ultraviolet, but it does because doesn't it give us the...
Yeah, some of it does pass through. So, like this no kind of... I think that this graph is a little funny because they don't have like these nice gray areas. Like I guess this could be a gray area.
It's a
maybe
gray area.
It's like
Yes, no.
it's kind of like it passes through, but not very well.
So is that where should the ultraviolet be?
Right. Ultraviolet. The stuff that's really bad for us that kills us doesn't pass through because obviously if it did pass through, we wouldn't be alive. So we wouldn't have this conversation. And the stuff that really just gives a sunburn, that can pass through. But we need that stuff too. So we need it in moderate amounts. Alright. But when it goes back, it's a different wavelength. It's the same amount of energy. But here's the problem. Alright. Let me do another analogy real quick and then I'll tell you what the problem is. So we talked about factories and cars, and we were talking about like cars going. And you guys ever drive? You guys drive at this point? Tiger, do you drive?
Not yet.
All right. You ever hit potholes? Like potholes are terrible in Hawaii.
So yeah, I know it is.
Yeah. All right. So you know what a pothole is, right, Tiger?
Yeah.
And it happens particularly after it rains. Now, it happens because of this process called weathering, and what happens is the wet rain gets in there, and then the cars go over it. But a certain size pothole will make a difference depending on the tire that you have. If it's a small pothole, no one really cares, right? If it's a large pothole, now you could do one of two things. You could either go really slow, and then your tire will go into the pothole and nicely come out of the pothole.
We hope.
You could go really fast, and what you would do is you kind of just like jump over the pothole. It wouldn't really like go into it. But if you're going at the wrong speed, then what you could do is you're not going too fast, you're not going too slow, you're going perfect for the pothole to mess you up. Your car will actually go into the pothole, and your tire will just go boom, and it will actually dent your rim. And that's a big problem, because then you got to get a new tire and a new rim. Now, new tires are like $400 for the pair.
Yeah.
New rims, on the other hand, are like $400 for the rim. I don't even know how much they are. Don't even want to buy one. It scares me. So there's this idea of there's this like perfect speed. There's this perfect speed for the sun to be able to penetrate our ozone and our atmosphere. So short radiation from the sun, it doesn't really it does interact with the clouds, but it doesn't really interact with the ozone. If it's going at the perfect speed, if it's too slow, or if it's too small wavelength, where it's too too high of a frequency, then that interacts with our ozone, and then the ozone just kind of kicks it out. Cool. Now, so that's when the sun's coming in, but when the sun's going, or when that energy that came in from the sun is going out, oh well, those are longer wavelengths, and sometimes those can interact with the stuff that we're in the atmosphere that we're calling greenhouse gases. And what happens when it gets captured, those greenhouse gases capture the energy that's supposed to be radiated out.
Stores it there, makes it move on.
We'll start collecting it. And then our atmosphere is going to do what?
It's going to heat up.
It's going to start to heat up. That's what's going on with global warming.
I'm wondering,
You're wondering what?
if we're in the atmosphere, we're protected from the gamma rays. You go to space, there's no atmosphere around. So people on them, like, if there to be a space expedition, say, or even on the International Space Station when they do spacewalks,
Yeah.
are they prone to gamma ray?
There's an incredible amount of shielding that you need to protect yourself with when you're doing spacewalks. The reason why, what limits the astronauts' ability to do spacewalks is the gamma rays, is those really bad rays. That is the killer in space.
So if it wasn't like that, you could literally kind of go.
So yes,
spacewalks
if you go outside in your spacesuit and you have enough of a spacesuit, enough of a protective layer to maybe like, if you have a big, I don't know, plastic bubble that's strong enough so that the vacuum of space won't pull it apart, but it's really just a big plastic bubble, and it has air being piped into there so you can breathe and whatnot. You'll still die. You'll die from cancer because those gamma rays are going to mess you up. So we need to put shielding inside of our spacesuits. They're not going up there in wetsuits, buddy.
Oh, I thought they were just a suit you go on. What those suits are like specially made to stop gamma ray?
They are, and they have, and the way that they stop them is these wavelengths are going into so they put in stuff that is like perfectly at that same wavelength, and it kind of disrupts it. It bounces off.
Oh, I kind of wonder how that works. Like, what do they put in to actually?
You want to know something? I don't know.
Okay, let's find out.
I wish I did. All right. Anyway, The if we go on to mention a bunch of this kind of stuff, that's cool, and then we talk about the Air Force and much of the details of the interaction of radiation and gases in the air was done by the Air Force after World War II because they were doing heat-seeking missiles, like we talked about earlier. And why would they do that? Well, because the heat-seeking missile, what's the principle behind this? And dude, you're going to be in the Navy, and you are in the Navy, and you're going to be a scientist, or maybe one day aspiring to be a scientist in the Navy, and you might develop these kinds of things. Well, what is the eyeball for the heat-seeking missile? It's an infrared camera, right? Yeah? All right. The problem is, yeah, it kind of looks like this, and then it's basically looking for, like, let's see where's the heat signature of the engine. Oh, it's there. That kind of stuff. But the problem is, what happens if this thing sees like a blurry picture? Why would it see a blurry picture? Well, because the greenhouse gases and the water vapor that is blocking some of the wavelengths that is absorbing, it's absorbing all this radiation, and it could mess up your sensors. So they did a lot of this science to try to figure out.
So they need to put something where the camera can see past those stuff.
Or make sure that they can distinguish between infrared from greenhouse gases and infrared from the engine of a jet.
What does the sun look like through those lenses?
I'm sure it looks like a big, I don't know.
Completely white.
Yeah, I'm sure that they tend not to like looking at the sun because it's just gonna white out their thing.
Yeah, but I mean, just imagine you're all lined up for a shot and then you fire it straight aimed at the sun because that's where the plane happens to be.
Yeah, well, maybe I wonder if like that's a technique. I don't know if that's a myth or a technique.
I've heard that before.
If you're being tracked by a heat-seeking missile, go towards the sun because then the thing won't really be able to figure out what's going on.
Or they can hit a button that sends out a flare.
Yeah, the flare probably works a lot better.
Yeah.
But and then what would be interesting is like maybe you can either be design the thing that says, all right, don't be tricked by the flare, or you design the flare and then make sure you get something that's super hot that looks like a.
I don't get why they call it infrared flares though. How is it infrared?
Infrared because what you're talking about is when we're looking at this thing right here, infrared light is mostly heat.
Oh, so it's just heat that distorts.
Like your infrared signature, like when you have night vision goggles on, right?
Yeah.
Put on night vision goggles. What it's seeing is the heat signature off of your body, and it's basically at a lower. If you were an animal, and there's animals that can do this, that can see lower than the visible light spectrum. We call it the visible light spectrum because that's the visible light we can see. It's not the visible light spectrum for everybody because certain animals can see different things, like the predator. Anyway, but if you were a different animal, there's certain bugs and certain things that can see in infrared light you would be able to see at night, and you see heat signatures. So the reason why they call it the infrared flares is because it's releasing a heat signature, and the missile is trying to follow the heat from the engine. So if you throw it off by giving it another shiny spot to follow, then it will try to hopefully that will save your butt, like literally, because the missile's gonna.
So it would be like
kick your tail.
The night vision, it sees just the heat radiating off of your body.
Yeah, that's exactly it.
So in a thermal, it sees the direct heat coming from it, or is it just more amplified night vision?
Thermal?
Yeah, like a thermal camera.
I thought it was the same thing. Thermal and infrared cameras are the same thing.
Oh, I thought we were talking about night vision. But
aren't they the same thing?
No, they're a little different.
All right. 1 second. I'm so sorry, you guys. I keep on getting calls. Let me take this real quick. Hold on. What's up, dude?
Yo, so I have to ask, what is that grade check 20140107 and all that?
Oh, that basically tells me that was that student's grade on this date. So that was last week's grade check. And then, the reason why I put that is mainly because it helps me track what the student, like, did the student go from a 60 to a 70 to an 80 to a 90? You see what I mean?
Oh, okay.
You can delete it if you want. I don't care.
No.
That's what it is. All right. Okay, bye.
Okay.
All right, I'm sorry. So we got to talk about the rest of this stuff. I'm sorry, we're running out of time. All right. So the Earth's climate is actually set up to kind of have these stabilizers, and it basically will help stabilize this imbalance. But the problem is we're outdoing those stabilizers. We're making things happen faster than the stabilizers can keep up. Because warmer things begin to radiate more energy very quickly, the Earth's climate is very stabilized, as noticed by the simplest climate model. But other processes may stabilize the system by reducing changes or destabilize it by amplifying the changes. The problem is, when we have certain changes in the Earth, these things that will help stabilize us will actually, there will be a big problem with it, and all of a sudden, all of this thing will spike really fast. You guys can read this. To be honest with you, it's not necessarily something I'm an expert at. So I kind of, there we go. Keep going down to the bottom of this document till we get to the spiky things that I want to talk about real quick. All right. So the Earth is warming, as we've kind of shown in the evidence. The pattern of this warming in space-time matches pretty much the expected. Or where did all of this stuff come from? Well, it kind of matches the technology changes in humans. So, how did we measure this thing from 10,000 years ago? Well, what we did was we didn't do the ice caps, but yes, I guess we went to the ice caps and we dug a hole very far down, extremely far, all the way to the bottom, as far as we could possibly go, miles and miles deep. And what happens is different amounts of carbon dioxide, whatever amount of carbon dioxide is in that atmosphere at that time and during that year will, it will change the properties of the air, hence changing the properties of the snow that falls. Hence we can tell, based off of looking at that type of snow and measuring the atmosphere inside of that snow, what the atmosphere was like at that particular time. And when we take a core of ice going straight down, the snow will fall on top of it and freeze, and fall on top and freeze, and fall on top and freeze, and fall on top and freeze. So we take a core that hasn't been contaminated, then you can actually measure what the atmosphere or what these things were from 10,000 years back. And then as you get towards the more recent years, between the 1800s and the 2000s, you can use your sophisticated instruments to measure it very accurately. But for the most part, see this orange or this purple thing is using ice core samples. And so here's a big ice core sample that we use, and here's another one that we use, and here's a bunch of other stuff that we use. So you look at carbon dioxide, and then we're going to look at methane and a little bit of, I don't even remember what that was.
Nitrous oxide.
There we go. Nitrous oxide. It's laughing gas. You look at the carbon dioxide, and what happens is you can see this giant spike that happens right over here. Boom! And what's going on there? Well, you've got the Industrial Revolution kind of happening right around here. And it's spiking up. So you can actually see the carbon dioxide, messing with this stuff.
Mm-hmm.
By the way, I remember what they were talking about with stabilizers, and I realized, you know what? It would be fun to do an experiment with you guys. And I hope that I'm making sense when I talk about this stuff. But let's talk about this stabilizer. In fact, I hope I have all the equipment. Can you give me a second? I'm going to go look for something. Give me about a minute. And I'm going to show you guys something, and then I'm going to leave. Or I'm not going to leave, but I'm going to have it on.
Oh dear. These famous last words.
I'm going to drink something.
Oh, what? I don't have any water on me, sorry.
No, here.
Edge.
Phone.
Well, not on the the edge as opposed to a corner, so that's not quite as bad.
That's good.
It's not,
I've dropped this so many times before.
What is that?
My phone.
yeah, just don't ever crack the screen. I think it's a pain in the
I
neck.
cracked the back pocket.
No, I have fun
Alright.
replacing an iPad screen. I believe I still have the burn marks on one of my fingers.
Oh, you smooth it.
No, what happened was I had to heat the adhesive, and in the process it heated the metal file.
Oh, so you're trying to burn.
Yeah, so I have a nice blister here. There's
There we
another
go.
one where I put the file through my thumb, and then I think I have a glass clip which finally got out.
Wait, why would you have to heat up the
Well, you have to heat the adhesive because basically iPad glass is attached to the frame for using.
Oh, so you have to break these. Oh.
Yeah, unfortunately you're going to destroy the old glass in the process.
So you have to replace it or something.
So that thing is a complete another pain, so please don't crack that screen. Or you can have Apple do the same thing for like 3 times the cost.
Yeah, that's true.
But it's gotta be sitting there with a hair dryer going, are you hot enough yet? Are you hot enough yet?
Alright.
Are you sure that's safe to drink?
This is not safe to drink. I'm going to do an experiment. I'm going to show you guys something. I need to grab a few things, but I wanted to show you that I kind of think I have all the right materials, and I kind of think I remember the science from this. But I need to wash this out and fill it up with water. This is not safe to drink. This is a pH test solution
Actually,
thing.
if
This
you
is
rinse
what
it
you put
out,
inside
the
of the
women's
thing.
bathroom is a lot closer than the men's.
Alright, and then rinse this out, put water in. I'll go to
How
run
much
downstairs.
water?
And I have a shell
How much water?
that I found. So I'll be right back. Let me just go grab this stuff. How much water? We don't need a whole lot. Just and then just put. And then if you have too much, I'll dump it inside this cup.
Okay.
All right. Let me go grab a straw real quick. Where do we have straws? All right, no straws. Ah, this will work. Okay. Okay, let's see. Have I done this with you?
I don't remember. Water.
In the engineering perspective, this glass is twice as big as it needs to be.
Oh, that's a lot. Alright, let me see if I can do this. I think I remember. Alright, so check this out. I have water right here. You guys see it? Can you see it? Yes?
Yeah.
Okay, I feel like I'm going to talk to you guys, so please talk back. Alright. So this is a pH test solution
It's gonna
thing.
be really acidic.
You think so?
Right when you hear tap water, it's gonna be acidic.
I hope it's not that acidic.
I hope not either, because that's what I've been drinking.
Okay, maybe a little acidic then.
Alright, there we go. You see it? Here, let me turn on the light. That way you can see it a little bit better. Alright, so what do we got here? In fact, I'll move out of the way so you guys can see a white background there. We got a blue, right? And
Yeah.
that color, light blue, actually I don't even have the indicator on it, is basically telling you that this thing's about neutral. It's actually a little bit on the acidic side, so it's not that great. But anyway, let's take a straw, which I don't have a straw. I got a little syringe over here, and I'm going to blow inside of it. Watch it closely. Ready?
Is it changing color? Or is it just the light that I'm looking at?
Did it change
It
in
did
color?
change color. Okay. I
Yeah.
thought it was just the light.
Yeah, it looks like it's getting yellow.
It's yellow. So I added more carbon dioxide to it.
Is that from the, is that due to oxygen or carbon dioxide?
The carbon dioxide, I don't breathe out oxygen. I'm sorry.
Well,
Free.
technically you do, but
A little bit.
And what is that?
technically you do breathe out oxygen, but I believe you breathe out more carbon dioxide.
Right. Okay, fine. I'm adding carbon dioxide. So all I'm going to do is I'm going to take this shell, put it inside. I'm going to stir it up a little bit. And I don't know if this will work, but we'll see. I know it works with coral. But I went outside and I asked, hey Sarah, do you have any coral with you? And she's like, no, I have a shell. I was like, oh, okay, let's try using a shell. Hold on.
think I think I know what you're trying to do, and please don't put water on the computers.
Alright, hold on, wait 1 second. I'm just getting it nice and soaked in there. Come on, buddy.
I think you actually need coral.
No, it should work. You can kind of see it.
What is it supposed to do? Change back?
It's turning a little bit.
Uh,
I think if I leave it in here, then
Yeah.
you're gonna be like, oh, hey, wait, I can see it after, like an hour.
yeah, if we don't have an hour, unfortunately.
Alright.
And I left my time machine at home.
So, here's what they mean by stabilizers. There's Earth has stabilizers. Can you see it? It's turning
Yeah,
from like
it's
a
like
yellow to
green.
almost like a darker greenish,
Yeah.
which means it's, you can't see it on the thing. The camera's not that good. Can you see it?
Not really.
Kinda.
Yeah.
Yeah, don't worry about it.
What about now, when it's behind my blue shirt?
Gee, wait for your results.
Yeah, I know. Anyway, what happens is the coral in the ocean will stabilize the amount of acidity that is going into the thing. What I actually did was I was creating more like acid, putting acid in the water, which if the clouds, or if the sun drinks it up and puts it in the clouds, and you get acid rain and all that kind of stuff, it's bad. It kills things. But the coral, nicely to say, good old coral, donates some of its calcium inside of it, and that calcium will create calcium carbide, which is, not as acidic, and then therefore you're turning the ocean back into a little bit more neutral.
You can take all the lemons in the world and drip it into there.
You take all the lemons in the world, you run out of lemonade. You make the biggest vat of lemonade you possibly could. But
Fish flavored lemonade.
sure, it would make it more acidic, fine. But the coral, the reefs and whatnot, will actually make it. Oh, there we go.
Let's try it. I can see it.
You guys can see it. It's turning a little bit more blue.
Trying. It'll get there.
It's going slowly. It's not as clear or almost yellowish as it was
It
before.
was before.
So this is a good thing, right? Like, we're stabilizing the ocean water. We're preventing it from getting too acidic. No, my friends, it's a bad thing. Because what did the coral have to do? Well, it had to kill, you killed part of the calcium inside of that thing. You're disintegrating it, literally. So yes, there are these things inside of the ocean called coral reefs that will protect us from being super acidic, whatever. But in the process, you're killing the coral reefs while doing that. What does that have to do with the Earth, with global warming and whatnot? Well, the same processes happen when you're talking about, these stabilizers and these amplifiers. Those same processes happen when you're talking about global warming. And yes, there's these stabilizers in place that the Earth has, but the problem is you're using it up too fast and you're killing it down. And so eventually it won't stabilize, and then you got a problem. Because what happens? What happens when all of this, the calcium dies from the coral reefs? Well, you end up getting white coral reefs. You ever seen those things? Like just pure white.
It's a good idea.
Those are dead coral reefs. So you just killed it. You killed this animal.
So
That's
like
a good
all those rocks are just all the coral rocks you always see in the road.
Yeah, you ever notice the coral rocks inside the beach? They're all white. They're dead. There's still
I don't
calcium
know
somewhere.
if it's too. I don't know if it's too common on Oahu, but on a lot of the roads on the Big Island, people will take coral rocks and
Oh yeah. No, that's
out of it.
that's straight up graffiti. No, yeah, what you're talking about is like you're talking about like when they take the white rocks and they put them on top of the black rocks and then they make their little signs and whatnot. I love it too because I think that technically it is illegal to do that because that's like graffiti. That's what they technically consider graffiti, and they always put their names. Like Sam Jones was here. Really, Sam Jones? You want to do that? That's pretty dumb, because if I were a cop, I'd be like, Big Island is not that big. I mean, at least there's not that many people,
What if it's
Sam
terrorist?
Jones.
Sounds like a
Mhm.
tourist.
Yeah. And I'm sure that people who live there on the Big Island are like, we don't do that. That's all the tourists. Yeah, I know. I did that when I was a kid. But anyway, yeah, the white rocks is usually the coral rocks, and the coral rocks is usually dead by then. It's on water and everything. We cool?
Mhm.
Do you understand these stabilizers? Please read this lesson because I think it's really good. It's a little bit convoluted when you read it. And this is the last time we're going to be talking about this stuff because we are moving on to a Python programming assignment that we're going to work on. We're going to team build a program, see how we can do it. We coolios with that? All right, my friends, thank you for letting me rant for an hour. Because that's what I've been doing. Talk to you later.